Welcome back to my series on multimodal embeddings. In this third part, we'll be using CLIP to detect objects in video. I'm Alex. I'm a data engineer, and on ZazenCodes, I'm teaching full stack data science. If you like the videos I'm creating here, then you can check out my premium content over on Patreon, and you can sign up for my weekly newsletter on Substack in order to support the channel. What's the point of object detection for video? I imagine there's a ton of niche use cases out there, and if you're watching this video, maybe you're working on one of those. So I'd love to hear what that is. Please let me know in the comments below. The most obvious use case that comes to mind for me is autonomous vehicles. Cameras on the cars need to be able to detect objects in their surroundings in order to drive properly. Another use case is surveillance security, being able to watch security footage of a camera and detect when something unusual is happening automatically. Content moderation, for example, being able to flag inappropriate videos that are uploaded to a social media platform. Manufacturing, monitor production lines for quality assurance or anomaly detection. Satellite monitoring, for example, being able to track environmental changes or detect natural disasters. Wildlife monitoring, observing animals in their natural habitat. That leads us into our demonstration for today. I have a 30-minute video on African safari animals in their natural habitat, and we're going to try and detect those animals in the video. In order to do that, we'll first compute embeddings for screenshots taken at each second interval in the video. First, we load our video and start iterating over the frames. At each second interval, we capture a screenshot, and then we use CLIP to generate the embedding for that image. With our screenshot embeddings ready, we can search over them for the presence of particular objects. For example, giraffes, lions. Here's a step-by-step process for doing that search. First, we generate embeddings for the text that we want to look up. For example, the word lion, or maybe a photo of a lion would be good. Next, we compute the cosine similarity of that text embedding with the image embedding for each frame in the video. At this point, we'll have a score for each frame in the video. We're going to plot this, and we'll see that it's a pretty noisy plot. And what we're going to do is smooth that out and then use SciPy to identify all of the peaks in that chart. And those peaks are going to correspond to the times when it's most likely to find that object in the video. Lastly, we're going to display these results and see how well we were able to do. All right, let's get to the demo. And make sure you stick around for after the demonstration, because I'll be talking about some computational considerations of doing this sort of thing in real-world situations. For example, when you have longer videos or bigger videos or more videos or many more objects to detect in those videos, and you have to do this type of thing in a timely manner. I would encourage you to follow along, and what you can do is grab this Git URL from my Git repo and say git clone like this. And once you have that repo, you can just go into it, ZazenCodes YouTube, source, multimodal embeddings, and this is where we'll be working. And so you'll see these requirements files. And what we're going to do is install a virtual environment for this particular tutorial called requirements video. Let's take a look at that. We're going to be using PyTorch, so I have Torch and Torch Vision, and then I have this CLIP repository that I'm getting from GitHub. So if we go there, you can see the installation instructions are just like this. So that's what I've included in my requirements file for that one. Python-m, I'll call it venv video. Open up VS Code because that's what I use to run my Jupyter notebooks. When I try and start running it, it's going to ask me to select a kernel. Find that virtual environment that we just created. It was called venv video, which is right down here. And then I'm going to need to install the Jupyter notebook dependencies. And now I can run some code in here. So this was the requirements that we used. I have my data available on my computer, and I called it YouTube Nature Video here. I've also got this embeddings file. So I'll take a look at this on my system and show you what I'm up to. In here, this data folder, this one, YouTube Nature, is where we're in. And then I have these embeddings saved, but we're going to regenerate these right now. So I'm just going to clear those out, have this empty folder, and this is the video that we're looking at. So I can open that up on YouTube. We can check it out. bunch of shots of different animals, and we're going to try and pick these guys out. The first step is to process this video, importing these libraries we need. OS, CV2, image. We're going to take in a video path. This is going to be some string. I'm determining the frame rate and the frame count and the duration, and this is how we're going to iterate over our video. So I have this for loop here. I have something like this, range 1 of duration, and then this frame interval second. If we had a duration of like 30, let's say 30 seconds, and then we had this frame interval seconds of 1, what would this range object look like? I'm going to convert it to a list so that we can see it, and it's just 30 elements in this case. But this is what this third argument does in range. It will skip over things. So if I say 5 like this and run that, now we're skipping elements like in that way. The problem, I guess, with this method is you can't be more granular than 1 frame per second. There's definitely a limitation of how I wrote this loop. I grab this frame, I convert it to an image. So this is going to be like an image object generating embeddings for that image. And I do that with these 3 lines. First, I generate the inputs that I need to feed into my model. And then within this context of this torch, where I don't want to compute gradients, that's just what this means, I extract the image features by calling this model.encodeImage and feeding in the image input. These lines will also make more sense when you see what this preprocess and this model object actually look like. And you'll notice I'm feeding these in. So these are going to be coming from the outside world. Lastly, we are converting our embeddings to this NumPy array, and I'm just throwing it into this list along with a bunch of timestamps, and then we're returning that information. And then I have this little function just to save our embeddings, because we want to just write these all to a file, and I want these all as just one kind of big object, which I'm going to save as this PyTorch object on disk. And you can see I'm creating that object here by using NumPy to concatenate all of these arrays together, which at this point we have in a list. This is definitely not the optimal way to do things. It's just how I did things for this video. So I'm going to fetch our model, and here I'm using the clip library. So this is different than how we did things before. We didn't use this clip library, and I have CPU as our device, but let's explore if we have a different device available or what that would even look like. So if I say torch.cuda.is available, we can see if I have a CUDA device available. And for you might have that might work, but on a MacBook Pro, that does not work for me. I have to use this metal architecture, backends.mps, and I should see that is available for me. I could generalize that using some chunk of code like this. Instead of saying CPU here, I can just put in device. What I'm going to do is say copy this into a new window, and I'm going to scroll up so I can see this function. So I'm going to call this function. So I'll copy this over. Also, we're going to want its outputs. I want these outputs to be available, and then this is process video. That's my video. Okay, here we go. So model preprocess, these are available now, and I'm passing those in. And then this frame interval seconds I have available as a global variable. Get rid of that, and we can call this. So let's process our video now. This input image is not in the right format here. So if I have preprocess for some image, this should be an image object. So I actually need to open this file and see if that works. All right, so what do I get out of that? It's 3 dimensions. These are going to be our 3 color dimensions, red, green, and blue, and then these are the number of pixels in each dimension. The problem with this, I believe, is that it's not on GPU. If I just print its representation, you should see the device at the end here if it's on a GPU. So here's how we do that. I can say d.to and then device. Let's see if that works. So it's taking a while to write this because it's transferring all of this data from the CPU memory to my GPU storage. And so now it's reporting, okay, I'm using this MPS device as defined by my device parameter here. I believe this will fix our problem, the error that we were getting. So I'm going to come up and do that. So I'll send it to the device. This is going to map this input to our device. So I'll need to pass this in from the outside world. I'll come back down to where I'm calling that, and I need to add device as an argument. So let's try this. Now I'm not getting any output here. I definitely want to be able to monitor this. It's been 30 seconds and I have no idea how long it's going to take. So let's just stop this and get some monitoring in place. As I iterate over these frames, let's keep a track of this. So I'm going to say TQDM and just throw that into a list. And this is just going to give me a progress bar. Great. So I can see that this should take about 15, 20 minutes maybe. So let's leave that running. And once I get these out, I'm going to want to save them to the disk so I don't like have to redo this again. And I'll go ahead and save those embeddings. Go over on my right hand side. Here's that function here. And I'm just using the video name in the file name here. And then I have the embedding path, which I'm passing in right here when I call this. That has finished running, and I've saved my embeddings to my computer. So let's have a look at those. They should be in this YouTube Nature embeddings folder, and right here I've just saved this file, this PT PyTorch data file. It's only 3 megabytes, but it took 20 minutes to generate that. Definitely worth saving these embeddings that I have created. And the way I would load those, embeddings timestamps equals torch.load from this data here, and I'm passing in our video name right here. I've saved a file that I'm loading as a tuple of items. So this PT file actually has 2 different PyTorch objects in it. By the way, these are going to be like identical, right, to the outputs of our function above. But this is like a checkpoint if I wanted to rerun this. So let's have a look at these embeddings. We're getting a big array. They're this float 16 data type. Okay, let's look at their shape. We have about 1,800 images, and each of them have an embedding that's 512 dimensions. And I'll add a bunch of cells below. By the way, let's also look at our timestamps, and we just have numbers up to the final time of our video. And so if I look at the final element here, it's about 1,800, a little bit less. I could convert that into minutes. So I have 1 frame per second. There's 60 seconds per minute. So if I divide that by 60, I can see that our video is about 30 minutes long. SNS.hist plot. Now, I don't think this is going to work. Maybe I'll have to flatten these. Right, okay, so they're distributed around 0, and they're normally distributed, these embeddings. Now let's get started on our object detection. We have these video embeddings, and we want to be able to calculate similarities with text. So I have a function here that will do this. So this is like a 2-dimensional vector being compared to another 2-dimensional vector. And then out of this, the main thing we're interested in are these similarities. I'm returning those here. These are going to be like cosine similarity scores. And you can see cosine similarity is not defined here. We can import this from like a library. In previous videos, I used torch. So I said something like torch.nn cosine. So there's this way to get the cosine similarity. Let's just use that. So instead of defining it that way, I'll do this. I was doing it differently before. I'll show you what I mean. What I said was from scikit-learn import. There it is. Okay. But anyway, let's try it using torch. Also, I realized this text array is actually just going to be a list. This is not going to be a NumPy array. It'll be a list of strings, just a simple Python list of strings. So if I from typing import list. Now let's go ahead and call this. What type of strings do we want to check in this video? This is all of the stuff that we're going to be searching for in this video right here. And so I've got some African animals like a lion, a rhinoceros, some natural elements like sky, river, ocean, and then city objects like lamps or computers or phones, stuff we really shouldn't be in here at all. African animals list, and that should work for me. So let's see how this goes. Placeholder storage has not been allocated on MPS device. I'll just try sending them to the device. This is exactly what I did last time, and I'll need to know the device. So device in, we'll see if this works. It's mad at me because of the similarities line. And remember I said, oh, let's just use this torch function, but before I use scikit-learn, well, maybe that was a problem. I'm gonna go back to this scikit-learn one. Similarity, and down here, I'll go ahead and use that version of the cosine similarity, and we'll see if that fixes everything. Right, so now I'm getting the opposite problem. Because I put this to my GPU, this function is no longer happy down here because these text features on the GPU. So I've got to put these on CPU. Maybe that'll work. I'm really not sure. Looks like that worked. If I look at my similarities, let's see what this looks like. It's 8 different objects that I'm detecting, and for each of those 8 objects I have similarity scores for each second of my video, for each frame in my video. Generate a plot, plotlib.py, plot as plot, like that. And this is what my plot looks like. It's really noisy. There's also a lot of series going on, so it's pretty hard to distinguish anything. What we want to do is smooth this out. So this will take in our data, and I define some window size. This is the number of samples around each point with which to take the average to help smooth things out. And that computation is being done by iterating over the data, and then for each point in the data we look at that window around that point, and we call this numpy.convolve function and replace the data with the result of that around this window at each point, and it has this smoothing effect. Instead of passing my similarities in directly, I want to pass them through this smooth time series function. It's definitely smoothing out for us. I could call that again, and let's change the window size now. Let's look at a window size that's a lot bigger, and we'll see that this becomes even smoother, easier to identify these peaks. You can also see things like the crocodile is really low, like similarity scores. It's clearly much lower than the others on average. Something that is noticeable here, but not really like obvious, hard to actually understand at all. Now we can start to just look and understand things. Even this rhinoceros, we can maybe pick him out like right here. But rather than having to eyeball this and pick out these animals, we want an algorithm to do that. So we're importing find peaks from scipy.signal. We want to find our peaks, and we take in the smoothed scores. That's these guys that we're looking at. I'll iterate for each set of scores. This is going to be like an entire time series of data, right? This scores is an array object, and in there I'm going to pass that into the find peaks from the scipy signal to get all of these peaks out. And then once I have those peaks, I need to look at the scores for those peaks. So I'm going to get all of the scores corresponding to those peaks. So I'll actually like use a mask on this scores array. And I have a little bit of an extra logic in here. I'm sort of creating this filter. So I could express this as like a filter in this way. And then I could pass the filter in here. And what I'm saying is like, okay, I only want to look at scores that are above the average. So I don't want like anything down here to match, because scipy might identify these little things as peaks, but I only want peaks that are actually like above the average. Plot similarities with peaks. This is the function that we're going to be able to call and kind of iterate on and play with. Doing that down here, I get my smooth scores. Then I get my peaks by calling that function I was just playing around with. And then I call this function, one I'm about to talk about, where I calculate my similarities with the peaks. I pass in some animals, my scores, and so on, my timestamps. It's really simple what I'm doing in here. I'm just iterating over all of these score peaks, but I'm like attaching the text associated with them and the scores associated with them so that I can include that information in the plot. So here we go. Really messy looking plot, lots of X's all over the place. Instead, let's plot them individually. And that's why I have this plot subset parameter here. For animal in African animals, plot subset, and I'll just plot that one animal. So I can run this here, and we can now clearly see our peaks for each animal. Here's the lion, this is the zebra, this is the giraffe, and so on. Now I want to show you what happens with that filter if I'm not doing the thing where I only look at peaks above the average, because you'll notice all of these peaks look where we expect them. They're up where we think we have maximas that we're interested in. These are like local maximas in a signal, but there are like peaks actually lower down, and I'll show you how this works. So if I go all the way up here and I just adjust this filter, I'll have to do something like this, removing that filter where I look only above the average, and I'll rerun everything. And now let's see what happens. So now I'm identifying a peak like this. This is like clearly not a point where we want a lion, and all sorts of stuff. The cheetah down here, is scipy's identified a maxima here. There's other parameters in this scipy find peaks that you can play with, and this find peaks distance of 100 was really helpful for me. So let's say I put that to 1, and now we'll plot everything and see what I get. Is look at all of these data points. So that's why I did the distance of 100. So let's correct everything here. I'm going to get the filter back, and I'll run down and rerun this. And so these are the points we're interested in. This worked for my data set. Now what I want to do is find the actual timestamps for these things, converting these times in seconds to this time delta object. And then I'm just looking at the string representation of that. And it turns out the string representation of a time delta object in Python is a pretty nice representation, where you can clearly see like, okay, 3 minutes, 10 seconds. This is 27 minutes, 39 seconds. So these are the timestamps I'm interested in showing. Now what I want to do is render images of the video at each of these peaks to see if we're doing it right or not. I want to see if these animals are in our video or not. I realized I never did this. Like, I don't have the video frames available to me. I just have their embeddings. So I'm going to have a new function right here, which is very similar, but this one actually just captures those frames and returns them as this kind of NumPy object of all of our frames. I should have done this earlier, but I didn't. So I'm using this function to do that now. So I'll just define my video path, call this function now. This might take a few minutes. This is done, and let's look at the video frames. Again, I should have done this earlier. That would have saved me 15 minutes. So we have all these frames. For each frame, we have a video, which I've resized here. So I've taken the video down a little bit, so it'll be quicker to process later. And then for each set of pixels in this final dimension, I have the red, green, blue channels. I'm going to save it using Torch, cast it as a Torch tensor. I'll create a new folder in here, frames. Then I need this YouTube nature frames. This video name should be available. Oops, I did not spell. Now when I want to load this path, and I'm going to, put that into this test frame. All right, so loading my test frames in here. I do have a torch object here, and it looks like it's the same. And I'm just going to go ahead and actually load those and replace the same object. So this is dangerous because I'm kind of like blowing up that 15 minutes if something went wrong with the save load process. But it's important to do that because if I can't actually load this data and work with it in the rest of the notebook, what was the point of saving it? Maybe I'll try to do that later and then I'll get errors because this didn't work properly. It's always important to make sure your notebook is actually workable from top to bottom if someone was to just pick it up and say run all the cells. Let's look at one of these video frames. So I have image from pill library, and I can say image.fromArray, and I'll put in one of my video frame arrays. Let's grab this one here and see what that looks like. Because it's a tensor, it's not a NumPy object, it's not working like I expect. So in this line, I could convert this to a NumPy array. Let's do this way. I'm going to say NumPy.array, and this will probably now let this work. Okay. Okay, I don't know. Let's test how well let's test how well our peaks are working. And I've got a little loop that I'm going to run in order to do that. We're going to iterate over all of our animals and our peaks, and I'm going to resize the video a little bit and then slap them together in this grid. And if you watched previous videos like the ecom ranking example using clip, you'll see this, you'll remember this code. I use that there. Make grid, torch vision, I'll import my transforms as well. Let's try and run this. First animal is the lion. And we're getting out a bunch of images of, some of them are lions, some of them don't look like lions. For zebra, I can see the same. Some of these are definitely zebras, but many are not. Same with giraffe. In fact, only one of these is actually a giraffe. These results are not extremely encouraging so far. I'm going to make a modification to how I calculate peaks. Define something called a minimum confidence. In addition to looking at only scores above the average, I'm also going to be looking at scores that are above some minimum confidence. So just look at the y-axis here. So for the lion, a lot of these peaks are above 0.2. So maybe that's our confidence interval. Or maybe we actually only want these ones all the way up here. So we could say 0.24 would be our confidence interval. And if we go down to 4, that's going to capture these two peaks for the zebra, and it'll exclude all of the rest of these. And that's what this minimum confidence represents. I'm going to add in all of these other objects, so these city objects, these natural elements, in addition to these African animals. These are all of our results for all of our objects. Now, these are smooth scores, but they're still impossible to interpret because there's just so many series going on here. Let's just generate this style of plot for these guys. Okay, let's go for it. You can see with our new algorithm, we're only picking out points above our threshold. So many of these peaks are now being ignored. For the cheetah, actually, we weren't confident enough to call any of these matches. And if we scroll down, I'm not seeing any peaks being identified here. Let's use a different confidence. Say, let's set it to, I don't know, just 0.15. I run this code down here. We're going to see all of these guys now getting picked out. If I was to scroll way down, we're going to actually be seeing all these peaks are now being identified for like all these things. We're finding all these rivers, all these lakes. I want to be really, really careful with how we're setting this because I want to get good results. So let's set this to a confidence interval of 0.25, like the default one, and I'll rerun this for continuity. So I'm going to wrap this grid code up into a function so that we can keep calling this in the future. And this is just the same code that I talked about earlier in a functional format now, and I'll run that for our animals. For the lion, we absolutely picked out a couple images of lions. We've got some zebras here. This is definitely a rhinoceros, and these are baboons. So a 0.25 confidence interval did a fantastic job at accuracy, but it did miss a lot. So the precision is really high, but the recall is pretty low. We weren't able to find any crocodiles or any grass. I'm going to recalculate my peaks, and in this case, I'm going to set the minimum confidence to 0.24. Dial it down a little bit. So now we start to misclassify some things. Here we're thinking this cheetah is a lion. The zebra, we have more matches. We did get a giraffe, but now we're thinking these cheetahs are giraffes. We think this thing's a rhinoceros. And the cheetah was matched well. And we get some more baboons, but for some reason it thinks that lion's a baboon, and then still no matches for the rest of our stuff. Let's investigate this a little bit more, this behavior. And I want to see how our similarity scores compare to one another. We've got a lion, a tree, and a car. You can see the lion is, really obviously in our data, and then the tree and the car, much, much lower. In some places, it's more likely to be a car in the image than a tree. And we'd certainly expect to see some trees, so it's not doing a good job at finding the trees in our data set. We've got these natural elements. We're not doing a great job at picking out any of these things. And we could do the same thing with our city object. I'll bring your attention to the y-axis because at the end of the day, like these averages are what it's all about. Rather than these minor oscillations. And the averages of all of these are much lower than the animals, like this lion, which clearly is doing a much better job at knowing that that's in the shot. So with an idea of looking at now the averages for these similarity scores and being able to sort of rank all of these things, not in a visual way, but in a very like numeric tabular way, let's calculate the peaks for everything with no confidence interval. I actually just want to fetch all of these peaks. And now what I'm going to do, by the way, this is still implementing that sort of only above the average mechanism. And now what I'm going to do with all these peaks is calculate some summary statistics on those so that we can compare all of our data. And so here I'm calculating those summary statistics, explain what's happening, specifically this step. So I have these peaks. Let's look at those. All right, there's a bunch of list of arrays, but inside of these arrays, what are these things here? These are the x-axis marks corresponding to the peaks. So this effectively creates a mask of which I can apply to other data. So I have all these scores. These scores data are in something called similarities, and I'm iterating over those here. So let's have a look at this. I'm going to say similarities. And let's just focus on the first element of each. So if I look at the first similarities element, a big array of scores. These are the things on our y-axis, right? And the indices of these are the x-axis values. This is the indice mask, which I can apply to this, right into this cell. And what I would need to do is say numpy dot array. And if I run this, it'll actually mask this down to just those values. Once I have that, these peak scores, I look at the average and I put that into this average peak scores. So the lion has a really high score, and notice this 0.225 and 0.204. These are the exact numbers we're getting here from our loop. I don't know if these are sorted, so I could sort values by mean score. And I want to make sure that's not in ascending order. So now we're getting all of the top scoring things for the average. That being said, I'm definitely more interested in the mean peak score here. Now that's the thing I'd rather sort by. The ordering is quite similar. Since a lot of these natural elements that I want to try and find, stuff like grass, maybe mountain, definitely rivers should be in here. These all seem to have lower scores. Look at how these average peaks are actually below 0.2. Treat them differently than the animals if I want to try and find them in the video. I need to change the minimum confidence interval. So just focusing on natural elements, I'm going to calculate the similarities just for those ones. It's these natural elements. And this is lower. This is lower than I would ever want to set for the animals. We're not finding a lot. There's actually still not a river. Grass, we are identifying. A lot of these frames, we're pretty confident we have grass. This monkey's chilling and definitely hanging out on some grass. So let's try lowering the threshold a little bit more and getting some better matches here. I'm going to copy this, bring it down here, and instead of doing 0.2, let's just dial it down by just 1 and see if we can open it up a little bit. And indeed we can. So here's a river, definitely a river, picking that out. This one is not, it's probably misinterpreting the sky up here as a river. It's picked these out as mountains, which they shouldn't be. It has found this tree now. It's found this rock that this cheetah's sitting by. That's pretty cool. And with that, we have reached the end of the demonstration. By the way, I want to show you how big these notebooks are. So I have all these dev notebooks, which I've excluded from the Git repo just because of their size. And the notebook we just saved here is 300 megabytes. It's really big because of all this stuff we're putting in it. There's all these pictures specifically. The notebook you'll download from GitHub, I'm going to try and bring it down to like less than 50 megabytes just to keep the whole repo small. Come in here and remove a bunch of these outputs. Now, as promised, I'm going to discuss some computational considerations with running this sort of process at scale. If you're a social media platform where you have users uploading videos and you need to analyze those to detect for inappropriate content, what does this kind of problem involve? You need really high throughput, otherwise you'll accumulate this backlog and eventually videos will never get processed because the backlog is so big. So you have to be executing this type of thing in a timely manner. What are some considerations for scaling? GPU acceleration. You can leverage GPUs for faster computation of embeddings and similarity score. We did use a GPU in this demonstration, but I'm not convinced that I'm using it properly or to its full functionality because I didn't get a big speed up switching from my CPU to the GPU. This could be due to the small scale of my data, but also I'm sure I'm not writing the most optimal code for this type of thing. So that's probably the first easy win you can think about. The next two considerations I'm going to think about are scaling vertically and scaling horizontally. Scaling vertically, increasing your compute resources on a single machine or single node. So maybe adding more and more memory so that we can process bigger and bigger videos. But rather than doing that, we can do something like look at out-of-memory data sets. So just stream data in chunks from a cloud storage provider, so like S3, and in each chunk, we process that, and then we move on to the next chunk so that we don't overwhelm our memory resources on one machine. Another thing we can do is scale horizontally, batch processing and distribute the batches onto multiple machines. Tools like Apache Spark can distribute this workload in that way. And then this allows us to handle more data at once. For example, we could process many videos in parallel. This can help us not only generate embeddings for the videos, which we know takes a long time, but also comparing the text embeddings with those embeddings from the videos. And on that topic is the final part I want to talk about with scaling considerations, and that's how to do those vector searches on our embeddings. And so there's databases that are designed to do this type of thing. We can efficiently search through high dimensional embeddings and compare them for ad hoc search queries against those embeddings. So rather than storing these embeddings just on your disk on files, these PyTorch files that we were using, and then loading them into memory and doing these cosine similarities, you can do that all with a vector database that's optimized for doing those searches really quickly. As much as I love the applied machine learning ideas and the demos that we're doing in this video, I actually love the ML ops side of things even more. And so if you'd like to see that kind of thing, please let me know. Give specific examples of the type of demos that I can give on that topic. To recap, we took a 30-minute video of African animals, and then we cut that video up into 1-second increments, and we calculated the image embeddings and compared those to text embeddings to generate scores. And from those scores, we identified the peaks in order to do object detection in video. Now, in the next and final video in this multimodal embedding series, I'm going to continue using CLIP to do object detection. In this video, I'll be fine-tuning CLIP on a labeled satellite image dataset in order to create a custom satellite image analyzer for my use case, which is identifying if an area of land is flooded or not. This is not something CLIP knows about because it wasn't trained on satellite data of flooded land versus non-flooded land. And so it's a perfect use case of fine-tuning. It does really, really well at this. I was amazed how well it did. So you can find a link to that video on the screen right here and in the video description. Thank you for watching, and namaste.